Hi guys, this is a video on C++ class templates. This builds on the previous video that was about the rule of three. Okay, first off, let's talk about something called the modularity principle. This is a virtue or a good thing we would like to have in our code, is for our code to be modular. Modular code means that it fits together with other code cleanly. You can see on the right there a picture of some Lego bricks. So we would say that our code is modular when, just like a toy Lego brick, you can click it together with another brick, or you can detach it and click it together with a different brick. These combinations just work cleanly without a lot of effort or confusion. An example of a class that is not modular is the maybeInt class that we defined in that previous video. The problem is, it works fine if you maybe have an int, but what if I maybe have a different data type? Like maybe I have a string. I suppose I could go in and make a copy of my maybeInt code and paste it and rename all of the maybeInts to maybe strings. I'd have to go through and make a lot of changes. Everywhere int shows up, I would need to change it to say string. And that would work, but that would be kind of a waste of time and effort. That would be labor intensive to go through and do that copy paste and make all those changes. It's also tedious, and humans tend to find that kind of tedious search replace stuff kind of boring, and they tend to make mistakes because of that. It's also expensive because you're spending human time on this. So there's another principle coming into play, which I call the division of labor principle, which has to do with how you break up work between your computer tools and your human ingenuity. Let's define the term business logic in case you haven't heard that. The term business logic means the human meeting of algorithm data. So the data in your program ultimately is composed of data types like strings and booleans and ints. The reason why it's important to people is because it represents some kind of concept in the domain that you're modeling. It doesn't have to be a for-profit business, it could be a nonprofit too, but we just use the term business logic for that. So for example, we earlier had a class called date. Fundamentally, date is three ints, and as far as the computer knows, it's three integers. But the reason why humans care about three int string together is something like 2020-08-26 means a particular day, the 26th of August in the year 2020. So that's something humans care about. So programs that we run on our computer, they cannot understand this business logic. They also cannot design algorithms. It's just something they can't do. But what they can do is perform tedious, repetitive work flawlessly, quickly, and cheaply, right? You can run a program and it will just crank it out and do what it's told to. It will not make any kind of arithmetic mistake or oversight. It'll be fast and it's really cheap to run a program. Humans are kind of the flip side of that. They can understand business logic, like how to put three integers together to make a date, and they can design algorithms. However, for a human, that kind of busy work, like going through maybeInt and changing all the ints to string, that kind of busy work, it's tedious, it's error prone, and expensive. If you're paying a software developer to do that work, you're spending a lot of money actually on that work. So there's a best practice for how we should divide up labor between these two agents that are working on creating software, and that's automation. The humans should be the one thinking about the business logic and the algorithms, and the computer program should be doing the repetitive work. It's not always possible to achieve this perfectly, but what we strive for is that humans aren't doing repetitive, tedious, error-prone work. Anytime you find yourself doing that, you should find a computer tool to do that for you, automate it essentially. Templates are a part of the C++ language that combines these two principles of modularity and automation. So we had a problem where I had a code working, a class working for maybeInt, and then now I want a maybe string. And when I thought about creating maybe string, I found that I would have had to do that kind of tedious, error-prone, repetitive work. The way that a template works is that instead of doing that tedious copy-paste, search-replace work, a human creates a pattern for how to create a class. The pattern is written like this: the template class name, and then a open angle bracket, the less than symbol, and then one or more template parameters as they are called, and then a close bracket or a greater than symbol. So I can create a pattern for how to create a maybe class. That pattern has a fill in the blank called capital T. And I could substitute in int for capital T and that becomes a maybe int, or I could substitute in string for capital T, and then it becomes a maybe string, or any other data type I'd like. So the technical term for T is a template parameter. We're reusing the same kind of word that we use for a function argument. Sometimes we call the inputs to a function a parameter. So you can have a function parameter or you can have a template parameter. What it's really doing is this kind of fill in the blank process where a programmer can specify a data type to get substituted for T. The word for creating one of these variations of a maybe is to instantiate the template maybe. So maybe T is a general pattern or a general template that can be created for any concrete data type filled in for T. And if I fill in maybe with int filled in, maybe int is an instantiation of maybe. The technical term here would be I instantiated maybe to create maybe int. The compiler does all the work of filling in these blanks, and this achieves that automation that I talked about earlier. If I do maybe int, the compiler will go through and look for every time t occurs and substitute int in for t. And as a programmer, I don't have to do that manually. So we've achieved this kind of automation that we wanted. Here's an example of how I could refactor maybe int to become a template class called maybe t. Refactor just means I rewrote it to work in the way I want it to work now. I kind of did a rewrite where I fixed some deficiencies. So I have my class maybe declared here. There's a new piece of syntax before that line of code that says template type name t. And this template type name t is the part that is saying this is a template class, and there is one template parameter called t. You have to write type name here so the compiler can tell that this is a name of a data type and not something like an int value. It's a bit of a technicality, but you get in the habit of just putting type name here every time. I still have essentially the same member functions. There's the default constructor, which sets the value to be null. There's the copy constructor, which makes a copy using a distinct block of memory. But notice here that I don't say maybe takes a argument of a reference to a int anymore. Instead, I say a t. So rather than talking concretely about the data type int as an input to these arguments, instead I'm giving a t, where t is this template parameter. So capital T stands for a data type. Anywhere you would be allowed to write a data type, I'm allowed to write capital T. So for example here, when I allocate a new object, I don't say new int, I say new t. And the rest of the functions would be modified in a similar way. I put ellipses here just in the sake of space and time. I added another couple of functions. For example, Boolean is value tells you whether or not this maybe currently contains a value, and that's true that there is one if the value pointer is not null. Or an accessor function, otherwise known as a getter function, that returns the current value. Notice that it returns a t. It doesn't return an int, it returns a t. Over here on the right, we can see an example of how you would use this template class. So when I declare a maybe, I have to put the value for t in between the braces there, the brackets. Otherwise, the compiler won't know what to substitute for t. So this maybe int makes an a, which might have an int and might not. And you can put whatever data type you want in there, like maybe string. And I make another string and then assign them. All of the member functions work as usual. That was one example. Let me just tell you the general pattern for creating a template class. You start a class definition, not just with class and then the name you choose and an open brace, but before that you write an extra line of code that says template less than character, and then a list of at least one type parameters. You can put as many as you want in there. In practice, we usually don't have more than 1 or 2 or 3 in the kind of code we're doing in this class. So type name, type 1, type name T2. You can use whatever name you want. It doesn't have to be capital T. There's a convention in the standard library to use capital T for type, but you can use whatever identifier you want. T1 and T2 are called the template parameters. The compiler will substitute concrete types for T1 and T2. So int might be substituted for T1, string for T2, or whatever. The rest of the definition of the class, so everything between the braces up here, can and should refer to T1 and T2. So you're free to use T1 and T2 as if they were data types, and you should do that at least once, otherwise there's no point in having those template parameters. To declare a class name of this type, you do have to give specific concrete types. So you'd have the class name, the less than symbol, and then a comma-separated list of the type values to substitute in for the type parameters. And of course, the number of types here needs to match the number of types in the declaration.